When an object that can roll down a ramp is released from rest at the top of the ramp, whether or not it moves with pure rolling motion or slides depends on what exactly is the value of the coefficient of friction between the object and the ramp, and also how steep the angle of the ramp is. So for example, if you have a sphere that you release from rest so that point A is making contact with the incline, and the ramp is really steep and the coefficient of friction is really small, then the resulting motion will just be a slide down the incline, which is definitely not pure rolling motion. With a greater value of mu, or a shallower slope, less angle, then the result is that the object moves from its initial position and begins to roll down the incline, so that the distance, arc length from point B to point A represents the path length here, and now point B is making contact. A has advanced to this point, and next thing you know, point C will make contact. And if that's the case, whatever the instantaneous point of contact happens to be, then there's no slippage between the surface and the rolling object. So let's see if we can derive some sort of an expression that tells us what's the value of the minimum required coefficient of friction to allow for pure rolling motion. And actually, before we get to the case of rolling downhill, let's go over the case of rolling uphill. So for this object rolling uphill, it starts out contacting the ramp, moving upward with a velocity of v naught, and by the time it reaches point B, it's still moving uphill, but with a lesser velocity. And likewise, it's rotating about its center of mass with an angular speed omega naught in a clockwise direction. And by the time it gets to point B, it's still going clockwise, but with a lesser final angular speed. So that tells us is the linear acceleration is a vector that points down the hill. Even though the velocity points uphill, if it's slowing down, the acceleration points downhill. And likewise, even though the rolling motion is clockwise, because it's reducing, the angular acceleration, alpha, points counterclockwise. So we're going to attack this problem by considering what's the sum of all force acting on this rolling object, as well as what is the sum of all torque that's acting on this object. So let's draw in some force vectors and see if we can solve the problem. So the force of gravity pulls straight down, and it acts at the center of mass. Then there's a normal force, so the point of application of the normal force is right where the ramp contacts the wheel. So the normal force does not act at the center of mass. The normal force is acting at the contact point, although its vector does pass through the center of mass because normal force has to be perpendicular to the incline. And then there's one last force, and that's friction. So the friction force is kind of interesting. Let's see if we can figure out the direction of the friction force. We know where the friction force acts. Friction is also acting at the point of contact. But by the way, it's not kinetic friction because the object is undergoing pure rolling motion. So there's no slippage between the object and the surface. There's just a gripping that takes place. So it's a mu static that we're interested in. So let's think of it this way. We can always imagine the rotation about any axis we choose. So we can think of the center of mass as the axis of rotation, or we can think of the point of contact as the axis of rotation. If we think of the point of contact as the axis of rotation, then it makes sense that alpha points counterclockwise because, well, the normal force acts at this axis of rotation and points this way. The friction force, whether it points uphill or downhill, we just know it has to point parallel to the incline. the friction force also acts at this axis. And so when your lever arm is equal to 0, you have a non-torque producing force. So both friction and normal force, are non-torque producing about this axis. So the only force that remains is gravity, and gravity pulls downward, and it has a lever arm from the point of application, or from the axis of rotation to the point of application of the force. So if you try the right hand rule on this one and point your fingers in the direction of the lever arm, and then rotate your fingers until they point in the direction of the applied force, then you'll see your fingers are rotating in a counterclockwise direction, and so that's all perfectly fine. But what if we chose to think of the center of mass as the axis of rotation? It should still agree that the rotation, the angular acceleration, is in a counterclockwise direction. So when the center of mass is the axis of rotation, then it's the normal force and gravity that are non-torque producing, because both of those vectors align with the axis. So the only remaining force is friction. Well, which way would friction have to point to give you a counterclockwise torque and therefore a counterclockwise angular acceleration? You see it? The lever arm would point from the axis to the point of application, and we know friction's applied here, so the only way we get counterclockwise is if the friction points up the hill. So there we have it. And that's a bit counterintuitive. We always think of, or usually think of, friction as a force that points opposite the direction of motion. In this case, not so much, right? The friction points in the same direction as the velocity for this rolling object. So I'll let you think about that for a bit. In any case, now we at least have some force diagrams that we can use to figure out the nature of the net force and the net torque. So for net force, we can make a free body diagram and just replace the wheel with a dot. There's a force of static friction pointing up the hill. Normal force points perpendicular to the incline. And then we can break the vector mg into components. So there's a component mg sine theta that points down the incline, and there's a component mg cosine theta that points perpendicular to the incline. Normal force and mg cosine theta have to be equal. And so how do we compare mg sine theta with force of static friction? Well, we know the acceleration points down the incline, even though the velocity points up the incline. So mg sine theta must be greater in magnitude than the force of static friction. So that means the net force is the difference between the two. Take the larger of the forces, mg sine theta, subtract from it the smaller force, and you have the net force. And by Newton's second law, we can replace net force with ma. So we have ma equals mg sine theta minus the force of static friction. So let's keep that on hold and develop another equation based on net torque. Now when it comes to net torque, we have to make a rigid body diagram as opposed to a free body diagram. In other words, we need a diagram that shows not only what the forces happen to be, but where the forces are applied so that we can picture the correct lever arm. So if we draw our wheel one more time. Actually, in this case, you know what? Let's say it's a hollow sphere, like a soccer ball. Then we know I is equal to 2/3 mr squared. Okay, so just for the sake of argument, we'll imagine that this is a hollowed out sphere. There's the point where the sphere is contacting the ramp, and then we have a force of mg that points downward. We've got a force of friction that points up the incline, and we've got a normal force that points this way. And then we'll use the point of contact as the axis of rotation. So that means both the normal force and the friction force don't produce any torque because they have no lever arm relative to this chosen axis. So the only force that has the lever arm is gravity. So there's a lever arm of r, an angle of theta, and that theta is exactly the same as the theta that describes the angle of the incline. So torque is force times lever arm times sine of the angle between those vectors. And then, thanks to Newton's second law for rotation, we can replace torque with I alpha. So I alpha is mgr sine theta. And careful, we have the rotational inertia of a hollow sphere about an axis passing through its center of mass. We'll call that I naught. But we're not considering the center of mass as the axis of rotation. We're considering the contact point as the axis of rotation. So we have to use the parallel axis theorem. And from the parallel axis theorem, we can say that the new rotational inertia about an axis through the edge is equal to 2/3 mr squared plus an additional mr squared, which gives us 5/3 mr squared. So 5/3 mr squared alpha equals mgr sine theta. We can cancel out the m. We can cancel one of these r's, and then we get alpha is equal to, what is it? 3/5 g over r sine of theta. But that means if we have pure rolling motion, the equations that describe pure rolling motion go something like this. The displacement of the center of mass is equal to the number of rotations or radians multiplied by the radius of the object. And likewise, the velocity of the center of mass of the object. And keep in mind, as this thing rolls, the velocity of the top is twice as great as the velocity of the center of mass, and for an instant, the velocity at the contact point is always equal to 0. So when we talk about the speed with which the object is rolling up the hill, we're talking about the speed of the center of mass, right? And when pure rolling motion takes place, the speed of the center of mass is equal to the object's angular speed multiplied by the radius of the object. And in the very same way, the acceleration of the center of mass is equal to the object's angular acceleration times its radius. So, if we know alpha is 3/5 g over r sine theta, then the acceleration of the center of mass is equal to all of that multiplied by r, which just gives us 3/5 g sine theta. Okay, so we can plug that in for the acceleration into this equation and use it to solve for the friction force. So I have reserved some notes here for rolling downhill. Let me drag this out of the way. See if I can do that without messing things up too bad. Well, botched it a little bit. Let me take care of that. Okay, so I believe this was 3/5 g sine theta is the acceleration of the center of mass. So when we plug in and rearrange to solve for F, we get friction force is equal to mg sine theta minus ma, so minus m times 3/5 g sine theta. So 5/5 mg sine theta minus 3/5 mg sine theta gives us 2/5 mg sine theta. But I also know this about the force of static friction. The force of static friction is always less than or equal to the coefficient of static friction multiplied by the normal force. It's not a strict equality. Force of static friction, it ranges from 0 up to some maximum value, the maximum value given by the product of mu and n. So in other words, 2/5 mg sine theta must be less than or equal to mu static times the normal force. Now wait a minute, what's the normal force? The normal force is mg cosine theta. So the force of static friction is less than or equal to mu times mg cosine theta. Now I get to cancel out the m and the g, and I can divide both sides of the equation by cosine theta. And what we find is the coefficient of static friction has to be greater than or equal to 2/5 g tangent theta. Any less than that, and the object will not have enough friction to grip the incline, and instead of undergoing pure rolling motion, there'll be some slippage, there'll be some spinning in place, and the contact point will have relative velocity relative to the ramp that it's on. Okay. Well, what about the case of rolling downhill? The question is, what's the direction of the friction force? And what's the minimum required coefficient of friction to allow it to roll without slipping? So I'm going to leave it up to you to go through a similar derivation. What I'd like you to do is make a contact point, consider that to be the axis of rotation, and picture all the forces that act. So we know what they are: normal force, friction force, and mg. But try to draw vectors that represent those forces in their correct location and scaled to some appropriate length in order for you to make a statement of net force, and go beyond making a free body diagram and make it a rigid body diagram. You can actually draw the forces on this circle, and it can represent your rigid body diagram. And from the rigid body diagram, get a statement of net torque. Whatever the net force happens to be, we can set it equal to ma, and whatever the net torque happens to be, we can set it equal to I alpha. So again, imagine this as a hollow sphere, and then you're going to link whatever result you get from these two expressions based on the principle of pure rolling motion that suggests the displacement is equal to the angular displacement multiplied by radius. In other words, the displacement of the center of mass. The velocity of the center of mass of the object is omega times r, and perhaps more importantly to this problem, the acceleration of the center of mass is equal to alpha times r. If you take that into account, along with the work you get by considering the net forces and the net torques, you'll be able to determine what's the minimum required coefficient of friction for the object to not so much slide as it goes down the incline, but rather roll such that the contact point always has an instantaneous velocity of 0. The direction of the friction force can be determined based on the right-hand rule and considering the axis of rotation as suggested. So I leave it up to you. Good luck.